Sure.
Hello everyone. Welcome to the Theory Lunch. Today we have Guruganesh giving a talk about approximation algorithms for K clustering via local K median. Guru is a third-year PhD student at the CS department and he works with Anupam Gupta. His interests are in approximation algorithm, network design, and online algorithms.
Great. Thanks, Nika, and thanks everyone for coming. So everything I say today will be joint work with Anupam Gupta and Melanie Schmidt. And I also want to say that this is a speaking skills talk, so it won't be as technical as a typical theory lunch, but hopefully everyone will get something out of it at the end of it. So my title is Approximation Algorithms for Aversion K Clustering via Local K Median. So what I'm going to do is I'm going to try and parse each of those bits for you, and hopefully by the end of it you'll be convinced of the results. So what are approximation algorithms? So typically, most interesting problems that we want to solve are NP hard. And that means they're computationally difficult. But we still want to solve them every day. So people come up with heuristics, algorithms that they show that they perform well in practice. But what we want is some kind of a provable guarantee. So even if we can't compute the optimum solution, we can get close by. And this quest also sort of helps us understand what the limitations of computation are. So by understanding how well we can approximate something, hopefully we'll understand what can be computed quickly and what can't be computed quickly. Okay? And so that's the idea behind approximation algorithms. So here is what approximation algorithm says in terms of in a picture. So typically, you have a minimization problem. You could have maximization, but I'm going to focus on minimization problems. And you have op, which is what I use to denote the optimal solution. It's sitting somewhere on this real line. And you have some solution that your algorithm will compute. I'm going to use ALG to denote the algorithm that you produce or your algorithm. And we want to say that these two are close by. Okay? But the whole idea of approximation algorithms is a bit paradoxical, because you're saying that I can prove a guarantee with respect to something that's hard to compute. Okay? And this was at least paradoxical to me when I first saw it. But it turns out there's a sort of easy fix to this, which is easy in hindsight, which is that you don't actually compare yourself to opt, you compare yourself with respect to a lower bound on opt. Okay? And throughout this talk, what I'll be trying to do is for the problems that we're interested in, I'll be trying to come up with good lower bounds, or lower bounds against which we can compare. And that will be, so you'll be seeing this picture often. And what I would like to say is that the algorithm solution is only a constant times the lower bound. And I denote a constant by big O of 1, which is just a fancy way of saying a constant. Okay. Great. So now that's the first part of the title. So let's get to the second part, which is aversion K clustering. So this is a new problem that we sort of introduce. And this problem has the following input. So you're given a metric, and you want to partition it into K clusters. So a metric is just a set of points that satisfy the triangle inequality. So they sort of behave like distances. And the cost incurred by each point is the distance to the farthest point within the cluster. Okay? And the total cost is the sum of the per point-wise costs. Okay? So here is, let's do sort of an example. So if I chose this particular clustering, it would be that the points on the right, the farthest point within their cluster from each of them is 3 away. Okay? So each of them will pay a cost of 3. And similarly for the cluster on the left, each point, the farthest point away from it is 4 units away. So in total, you would pay 14. Okay? But if you chose a different clustering, so let's say we did top and bottom, then the bottom nodes, they're 4 away from each other, so the farthest they need to travel within the cluster is 4 units. But the top nodes, they're 9 units away. Notice that there wasn't an edge between them, but you would take the shortest path. And the shortest path would go via here. So the farthest point in this cluster from this point is 9 units away. Okay? Is this clear? So this particular clustering has a cost of 26. Okay? So why did we study this variant? Okay? It was actually given to us by Christian, so who some of you may know. And Christian works on extended formulation games. So that's things like poker and blackjack and things like this. And Christian likes to compute Nash equilibria. Now, if you don't know what any of these words mean, don't worry about it. All that, for our purposes, what that means is there's some tree, and there's some property of this tree which we call the Nash equilibrium. And Christian likes to compute this. The problem is, Christian works with very large instances. So when I spoke to him, he was like, my trees are usually of size 10 to the 8, 10 to the 10. So computing this Nash equilibria gets very hard when the instances are this large. So a very natural idea is to try and solve it on a smaller instance. Okay? And of course, when you try and reduce your problem size, you're going to lose something. And what you're going to lose is, when you come back, you'll get an approximate version of the quantity you're trying to compute. So you'll get an approximate Nash equilibrium. So a natural question is, how do I come up with a smaller instance? Okay? And Christian's solution was to cluster the children. So here we have 4 children, A, B, C, and D. And his idea was, let's just cluster some of the children, and we'll pick one representative from each cluster. Now, how good is this clustering? It turns out the quality of the approximate Nash equilibrium is denoted exactly by the aversion K clustering problem in a suitably defined metric. So let me parse this for you. All it means is you take each of these points and you map it to some space. And how far 2 points are in this space represent how dissimilar those children are. Okay? And it turns out that if you perform aversion K clustering here, whatever is the minimum cost, that relates to the approximate Nash equilibrium. That somehow relates the quality of the Nash equilibrium. Okay? Now, this was the problem. I mean, I'm sure there might be other ways of solving this particular problem, but this is how Christian and Thomas Sandholm solved their problem. And this is directly from their paper. Yes?
Can you comment a little bit about what is the mapping that you're doing here, and is it something that you can do in polynomial time?
Oh, definitely. So yes, so this is a mapping that happens in polynomial time. And I don't want to get into
polynomial size, this graph?
yes, because but I don't want to get into too much of how they particularly reduce their problem. But in some sense, they sort of give us a nice clean version, which is the aversion K cluster. And we just solved that problem. Yes?
Our visitor Sheng Tang proved that there is no approximation for this problem. That in fact, you can't do it, but this is mostly heuristic, right?
As in to compute these approximate Nash
No,
equilibrium.
but the Nash equilibrium problem does not lend itself to
Oh,
complete
that might entirely be
strong
true.
sense.
That might entirely be true. But I mean, Christian has to
That's all.
solve this.
That's what he was explaining to me this morning.
Okay.
That it's hard.
So I
Even
mean,
for 2 players.
fair enough. I mean, but Christian has to solve problems on a particular
I understand
instance.
practice, but I'm just saying that it's a heuristic as opposed to.
Oh, sure. I mean,
known to be-
sure. I mean, what I want to say is that the approximate, the quality of the approximation depends on how good you can cluster these points in this metric. So if your instance is bad, that just means that any aversion K clustering will have a bad solution.
But if I understand correctly, also this is not exactly a Nash equilibrium. It's a perfect game Nash.
Exactly. It's like an approximate version.
For
So
which that problem, I mean, if the instance is polysize, it's not a problem, right?
Right.
So it's not exactly the same as the classic Nash equilibrium.
right. I mean, at the end of the day, this is just the motivation. I'll say that the problem is interesting on its own right, but we had a motivation to solve this problem. It was given to us by someone else. Okay? And they solved this in practice. They used an IP, and they said the IPs tend to work very well. So in some sense, as theoreticians, we are tasked with the idea of explaining why supposedly hard problems are solved in practice. So that's at least part of the goal of this talk. Okay. So the thing about the aversion K clustering problem is that it's a bit hard to understand. It has this sensitivity property. And what do I mean by that is that supposing you had a lot of points clustered together, and you had 2 points far away. Now, if you had a nice clustering like this, everything would be great. But the moment you reassign 1 point, notice that everyone here, their cost has gone up, because everyone, their farthest point now is this much away. So in some sense, the cost has gone up exponentially, has gone up by a lot. So it could potentially, so this means that it's somehow hard to understand this problem. So what we did was we said we couldn't really understand this direct problem, let's study somewhat of a related problem, which is called the local K-median. Okay? So the local K-median problem, it's somewhat natural, which is that you're given a set of clients. These are the blue dots. And you're given a set of facilities. Okay? And you want to open the facilities so that you want to open at most k of these facilities to minimize the connection costs. Okay? Now, this is a very standard problem. The only twist is each of the facilities has a radius. Okay? And now each facility can only serve clients within the radius. Is that clear? So one possible solution here, so here's the radius, is I close these two facilities. This is what I'm going to use to denote closure. It's this little circle with a cross. And I open these two facilities. Okay? And now notice that everyone can be served within their radius. And this is a very natural problem. You can think of it as like wireless towers and clients. But despite it being so natural, it hadn't been studied before in the approximation literature. And it turns out for a very good reason. It's NP hard to even test if this has a feasible solution. Okay? And the reduction is not hard, it's just a reduction from set cover. But this immediately has some implications. So one of the implications is that, remember, we had this number line, we had opt sitting over here, and we had something that our algorithm would produce. But what this statement is saying is you can't even determine if opt is sitting on this number line, or it could be at infinity. Okay? And what that immediately says is that if you had any approximation algorithm to this, you could determine if opt was sitting on that line. So that immediately says there's no approximation possible. Okay? Is that okay? So that means that we have to give up something in order to solve this problem.
I'm a little lost, I'm sorry. So
Yeah.
You're saying something, so what do you mean by how to determine feasibility for local K? I understand that it's an NP-hard problem, but what is the decision problem? Does there exist
Exactly.
a subset of K of the towers
That
covers
can,
everybody?
yes.
And are we assuming that at least kind of like all of them will cover everybody, right? So if we have
Oh, no, you don't even have to assume that. It could just be that there's a client and no facility covers it. So in this case,
an easy no.
Exactly, it's an easy no. But even in the case where everybody's covered, like every client is covered by some facility, it's NP hard to determine if there's a solution. Okay? Is that okay? And because, you can't even determine this, there's no way you can approximate this. Okay? So you have to give up something. And what we give up is we give up this idea of locality. So that introduces us to this notion of bi-criteria approximations. So we say we have a rho-psi bi-criteria approximation. If the algorithm produces a solution that's at most psi times opt, but it violates each radius by a factor of rho. Okay? So let me again demonstrate this by an example. Here's an instance. There's two facilities. They each have radius 1. And there's one client sitting at the corner. Now, a simple solution would be opt equals 1. We just open this facility and we connect him here. This connection cost is 1. But I could be silly. I can close this down and I can open the other one. So notice that now he has to travel 3 times opt because his total distance is 3. But also he's violating this radius by a factor of 3. Okay? So that gives me a 3-3 bi-criteria approximation. So what's the connection? So this is the last part of the title. It turns out if you had a rho-psi bi-criteria approximation for local K-median, this yields a rho times psi approximation to the aversion K-cluster. Okay? So whatever you lose in the locality and the cost factor, you just multiply them, and that's what you lose for the aversion K-cluster. Okay? It turns out this proof is not very hard. You could even give it in an undergrad course, but we're not going to go into it because it's slightly tangential. Okay? But for the rest of the talk, my goal is going to be to try and come up with a constant by criteria for the local K-median problem. That's what I'm going to aim for. Okay?
What's your metric?
So it could be any metric. Okay? Great. So, as I said earlier, one of the key features of approximation algorithms is we try and come up with lower bounds against which we can compare. And sort of a time-tested way of comparing of generating lower bounds is the linear program. So we're going to try and do the same thing. We're going to try and write a linear program for this problem. Okay? So here's how I start my linear program. I'll have a set C for all the clients. I'm going to let F sub j denote the set of facilities that can serve a client j. Okay? I'm going to say yi, and yi is going to be 1 would indicate that the facility I is opened, and xij, and if xij is 1, that would indicate that client j connects to facility I. So these are the variables of my linear program. These are just sets that help me. Okay. So here's the constraints. The red constraint on top, it just says each client is connected to at least one facility. The blue constraint says a facility needs to be open if you're going to connect a client to it. Okay? And the last constraint says you open at most k of these facilities. Okay? And my objective is just going to be, I'm going to minimize the total connection costs. Okay? So this is the linear program that I write. And I'm going to hope that I can compare whatever I get to this quantity. Now it turns out LPs are like magnets. They come in pairs. Okay? So whenever you write a linear program, whenever you write a linear program, there's a mechanical procedure that you can do to it and get another linear program. And it's called the dual. And you don't really need to worry about what this is. All you need to know is that anytime there's a feasible solution to the primal, we're going to get it's going to be greater than the feasible solution to the dual. Okay? So instead of comparing myself to the primal, I can compare myself to the dual, because I know that the dual will always be less than the primal. So if I can compare myself against the dual, then I'm golden. Okay?
Why isn't it equal in this case?
Oh, good. So that's my next slide, which is that at optimality, they're equal. And this is like this amazing property. Okay? In some sense, the dual is what certifies that the linear program has achieved its optimum. Now, my idea was to compare against this thing. Now, the primal I understood. I had an interpretation for the variables. I understood what the constraints were. But the dual is just this weird object. Right? More importantly, it has these like funny negative signs at the top. Right? I don't really like negative signs because they make it hard for me to approximate things. So if they're going to be equal at the optimum, I'm going to wave my hands and I'm going to move it over. Okay? So I just moved it over the equal sign and now there's a plus. Now, for those of you who know linear programming, this is not really a legit thing to do. But while we're doing illegitimate things, two wrongs make a right. So let's do something else. This constraint looks weird, but it's saying that the sum of facilities is at most k. Let me ignore it. I'm going to move it to the top. Okay? Now, what have I achieved? I've just moved things around. Have I really gained anything? And the thing is, if this has a nicer interpretation, and the interpretation is, let's look at Z and let's treat it as the price of a facility. In effect, what I've said is, you don't have to open exactly k facilities. You can open as many facilities as you want, but every time you open a facility, you're going to pay a cost of Z. Okay? And now I'm going to try, hopefully, I'll assume that some paradigm of economics holds, which is if you increase the price of a facility, you'll try and open fewer of them. Seems like a reasonable assumption. Okay? So this gives me a strategy. Okay? Because if I had opened exactly k facilities, I could just undo all the mistakes that I made and everything would be golden. I would have had a solution with which I can compare myself to. It would have been a solution to my original problem. So I'm going to try and solve for the fixed value of z, which is find the right price. And the next step would be I can find the right price to open exactly k solutions. Okay? And if this strategy works, then I would have had a nice solution to the original problem, the local k-median problem. Okay? Now, once again, this is the LP. It turns out that this new dual has a nicer interpretation. It's also based in somewhat economics, but I'm going to skip it because it's not too relevant, and also I don't want to take up too much time. But the next thing was that two very smart people, Jain and Vazirani, they developed a nice primal dual algorithm for a fixed value of z. So they said, if you give me a value of z or a price for the facility, I can tell you what's the minimum number of facilities you need to open and how to connect them. Okay? However, one caveat of their algorithm is that it doesn't respect locality. They don't have these radii constraints. They just said any client can connect to anybody else. Okay? But if you look at their algorithm closely, it can be made to work in the bi-criteria sense. So what they do is that their algorithm will only violate the radius by a factor of 3. Okay? If you run the exact same algorithm. And more importantly, the total connection cost is bounded by this quantity. And if you remember, if this was k, this would exactly be my dual. Questions at this point? Yes.
It's really hard to see where this the relation, the factor of 3 is coming from. Because in the LP, you just have these sets fj, which are just these sets.
Exactly.
How would that translate to numbers?
And that's a good question. So if you remember the original example I had, where you had two facilities that were right next to each other, and I moved a client not to the current facility, but to its neighboring facility. That sort of violates by a factor of 3. So that's where it comes from. And their primal dual algorithm does is effectively, it opens a bunch of facilities, but it could have clients assigned to multiple facilities at the same time. So what they do is they'll just close one and then reroute everyone to the neighboring facility. And that's where this violation of 3 comes from. Okay. Any other questions? Yeah.
So I'm just trying to get the big picture. So originally you were using the LP as a way of getting a lower bound, right? And then you were going to get some kind of approximation algorithm to the LP, lower bound.
That's right.
You haven't done that yet.
No, in fact,
all you're doing is full-on lower bound now.
Exactly. So in fact, I'll tell you that I'll never solve an LP throughout this entire process. What I'm doing is I'm using the LP as just a lower bound. And what I do is I compare against something that looks like a dual. In fact, it is a valid dual, but it's never the solution to some LP. It's just some feasible dual. Okay? And that's what their algorithm essentially gives me. It gives me an answer, and it also gives me this dual certificate that says that you're not too far away. But you never actually solve an LP. Okay? Does that answer your question? Yeah. Great. So this means that, we're doing great, Our first strategy, the first step is solvable. So now all I need to do is find the right price of z to open exactly k facilities. Okay? And this is what I'm hoping for. I'm hoping that the algorithm's graph is going to look like something like this. As you increase the price of a facility, it's going to open less and less. And I can do a binary search and find exactly k. In this case, I would be done. I can go out. Now, of course, there's a reason I call it best case, because there's a worst case, and this could happen. It could be that there's no price at which you'll open exactly k. You can have these precipitous drops. You can have these steep drops. Essentially, as you increase the price, you'll open too many, and then all of a sudden you'll open too few. There's no smooth transition. Okay? And these instances do exist. You could construct such instances. Yes?
Which is also says the particular algorithm you're using is stable enough to actually be...
That's a great question. It turns out, this picture, it doesn't even have to be monotone. But I don't need it to be monotone, all I need to do, what I'll suffice with is I just need to find a point where it opens too few and too many for the same price. Okay? Let me make that more concrete. I can always find a value z such that you'll open too few at z, sorry, too many at z, and then if you move it a little bit, you'll open too few. And then my idea would be to try and combine them, so that I open exactly k, but I need to make sure I'm cheap. And what this means, I'll elaborate that in a few seconds. Okay? And step 2, I can do something like a binary search. Yes?
That epsilon there, is that just any, like what?
Yeah, I can do it within any polynomial factor of epsilon. So no matter how small epsilon is, as long as...
Which epsilon is the approximation factor for? Because we got psi and rhos earlier.
That's a good point. So what this epsilon will do is it'll blow up the epsilon in the cost factor. But I'm going to ignore this epsilon because I can make it as small as I want.
Oh, I see.
Okay? So no matter what precision you give me, I can get below that precision. Okay? Great. So this is my new strategy. I'm going to essentially get 2 solutions. One's going to open too many facilities. One's going to open too few. And I'm going to try and combine. So before I do that, let me define a very natural graph, which is, I call this the adjacency graph, which is I'm going to have one facility open for every solution, I'm going to have one vertex for every facility that was open in the first solution. And that's going to be the left side of my bipartition. I'm going to have one facility for every, I'm going to have one vertex for every facility in the right side of the solution. Okay? And I'm going to connect 2 of these if they serve the same client in their respective solutions. Okay? Is the graph clear? So let's just see what our earlier concepts would look like. The first solution, by definition, would just be I close down all of these facilities and I open these facilities. Okay? The guarantees that I had was that the connection cost was at most this quantity. Notice that there's a K1 here. And my locality is violated by a factor of 3. Okay? Similarly, I have a solution 2. And everyone would now move and connect to the right side. Notice that this is a K2 times Z. And locality is violated by a factor of I plus 3. Okay? Well, what would I would want my solutions to be cheap. So what would that entail? So these 2 kind of look like duals. Okay? The only problem is this is K1 and this is K2. So a natural idea would be to try and take convex combinations. And that's exactly what I do. I pick my value lambda just so that it'll turn it into K. And when I combine it, when I multiply lambda times the first equation and 1 minus lambda times the second equation, these 2 parameters will become K. Lambda times K1 plus 1 minus lambda times K2 would become K. So I would get this inequality.
This isn't realizable, but it's just so you can get a better load back.
Exactly, yeah. And notice that, so it turns out taking convex combinations of duals preserves being a dual. And if I go down, this is a valid dual. Okay? So this thing is a new lower bound for opt. Okay? So I know that whatever opt is, it's going to be bigger than this. Okay? I mean, there's a factor of 3 involved, but I'm not counting constants here. Great. So what I'm going to compare my out to is this quantity. And notice that this has a nice interpretation, which is that this is the average cost. In some sense, it's taking a weighted average of the entire costs. Okay? Great. So now, here are the rules for combining. I need to make sure I open K facilities from solution 1 and solution 2. I need to make sure that whatever facilities I open, they satisfy these locality constraints. And the total connection cost is at most some constant times this quantity. Okay? Great. A natural idea that's been used in the past is to do some kind of randomized rounding. Okay? This would just mean I would open facilities here at random with the right probability. I'll open facilities here at random with the right probability. But of course, this has problems. In particular, if you look at, say, you did some kind of rounding, and you close these facilities down. So you have these two clients that need to be assigned in your new solution. But remember, I need to make sure that locality is preserved. Everyone is only a constant factor away from some radius. But I don't really know much about the radii of everybody else. They could be violating their radius by a lot. So I need to be more careful when I'm rounding. And this is where we spend most of our work. We were trying to figure out how to round things so that everybody is satisfying locality and satisfying connection costs. Okay? But what is the best case scenario? Our best case scenario would be something like this. This is what the graph looked like. Okay? Because in this case, if k was 9, I would just close everyone here and I would just pick solution 2. But if it was 8, then I can close an appropriate number from the right, and I can open the adjacent ones on the left. And if it was like 7, I could do the same thing. So I could keep doing this. I can get any number between k1 and k2. Okay? And because if you remember, the lower bound was in terms of averages. If I make sure I always close down the cheapest such facilities, I'll make sure that the average of them will certainly be good. Okay? Now this is what we'll aim for, but our graph can look complicated. So we need to simplify this graph in some way. Okay? So this is sort of our first way of simplifying. I'm going to call an edge a downward edge if First, let me draw the graph in such a way that the radii are going downwards. So if you see a facility lower, that means it has greater radius than some facility that's higher. Okay? So I call an edge a downward edge if literally in this picture, when you look at it, the edge is going downwards. And this is with respect to some facility. So if you look at a facility, the downward edges with respect to that facility are the edges that are going downwards.
So you're sorting all of them? So like the one on the top right has the smallest radius, then the second, and then kind of like the third. So you're sorting all of them?
All of them, that's right. So this would be the smallest, it would be the second smallest, third smallest, fourth, and so on.
So it's not like you're sorting them individually? Just
No. This is, it maintains the radii with respect to both sides. Okay? So, and that's critical actually. So,
otherwise it doesn't make, otherwise downward doesn't make
yeah, exactly.
sense.
Otherwise downward wouldn't make sense. So downward just means that the neighbor's radius is greater than mine. Okay, that's another way of seeing it. Now I'm going to do, the first step that I'm going to do is let's zoom in on a particular facility. And I'll look at all the downward edges with respect to this facility. And I'll reroute. Okay? So I'll take the bottommost one and I'll move it to the topmost one with respect to the downward edges. Okay? Why is this a good thing to do? Well, once I do this, the new graph would look something like this. Okay? Now, a good question would be, why is this a good thing to do? Well, at the end of this, what I'll do is I'll maintain that each vertex has only one downward edge. Because if there were multiple, I would sort of combine them to the topmost downward edge. Okay? And by doing this, I ensure that the graph has no cycles. Well, why is that? Well, one way to see it is if you had a cycle, look at the topmost vertex of that cycle. It would have to have two downward edges by the definition of topmost, right? But I just showed that this makes sure that the graph has only one downward edge. So what I get at the end is a forest. Okay? Right, so this is, so at the end of all of this, now I need to make sure that what I did was a valid move. In some sense, locality was a bottleneck in the previous step. I need to make sure that I preserve locality when I do this step. But this is where the definition of downward is sort of useful. What do I know about my previous solutions? Okay. What I know is that each of these clients is at most 3 times the radius from this facility. it's at most 3 times the radius from this facility. And this is at most 3 times the radius of I1. Okay? But, so the total it can violate is at most the sum of these quantities. But since the radius of I1 was greater than the radius of I, this whole violation can be at most 9 times. Okay? So essentially, I've come up with a new graph that looks like a forest, and it violates locality by a factor of 9. Okay? It turns out a similar argument works for costs, but it doesn't work for costs for the general local k-median problem. What it works for is the set of instances that come from my original k-clustering problem. But for now, you can assume that I get a cost and locality violation of 9. So I essentially get a 9-9 bicriterion. Great. So now I have a tree. A forest. And this is, we were stuck here for a while, but then we realized this is just, there's a property of forests. Okay? And it turns out you can always partition a forest so that the neighborhood on the right side is exactly 1 more than the neighborhood on the left side. And this is true just in forests. Notice that every forest would be bipartite, but in particular it's true for these types of forests. Now why is this useful? It's again useful because whenever I want, I can close down for whatever number in between K2 and K1, I can close down the right number of facilities on either side. Okay? And I can just reroute. And this rerouting is just, we're moving clients to what they were going to in one of the 2 solutions. So this naturally preserves locality. Okay? And this is, to come up with this partition, we have to look at the entire graph. Okay? We can't just, previously we were just doing local steps. In fact, for all the previous algorithms in this sort of area, they only do sort of local rounding. But this is, I think, the most interesting technical part of our algorithm. Okay? So we do a non-local rounding. Now, I want to say that there's a little bit of a caveat. We don't always find a partition like this. We find a partition that's good enough, usually. Okay? So in total, we can close down sort of the cheapest, we can close down the most expensive, and just by an averaging argument, we can ensure that we don't violate the cost too much. Because my original cost bound was in terms of averages. Okay? And locality is preserved just by the partitioning property. Everybody was going to a solution they would have been going to anyway. Okay? And this is the entire algorithm. So first, we convert our problem into a local k-median instance. Then we use the modified Jain Vazirani algorithm for fixed z. We find a value of z such that we open too few or too many. And then we combine them. And this combining is probably the most interesting technical aspect, which is we convert it into a forest, and then we do this non-local rounding. We find a nice partition, and we appropriately open and close facilities. Any questions at this point? Yes?
I guess regarding step 3, maybe going back a bit. So just to make sure I understand, so of course, even if you had K1, K2, even without the restriction of the prices being close, you could take a convex combination and get K.
Right.
Do you need the prices to be close because then the values of the 2 duals are very close?
Exactly. And yeah, that's precisely it. Because by ensuring that they're off by a factor of epsilon, my cost I can just push that epsilon into my cost. So everything here, there would be a plus epsilon type problem. But yeah, that's why I want the prices to be close. Yeah. Any other questions? Right. So, the algorithm is not too hard to state, at least. Well, what's the worst case analysis? This is the not ideal part. the worst case number is 216. So I can't really go to Christian and be like, this is going to change your life. Use this everywhere. But I will say that the worst case analysis is very pessimistic, in the sense that we spent a lot of work, in this case when you'd open too few or too many, but these instances are very brittle. Like you add a little bit of noise and they go away. So at least my intuition would say that the correct answer is like a single digit number, maybe 2 or 3 or 4 or something like this. You should be able to get a nice simple approximation number for this. Now, and this is not just for this problem, even for other problems like k-median and so on. There's a tendency that these worst case instances are brittle. And adding a little bit of noise removes them. But we just don't know how to add the right noise in some sense. But one thing that's very interesting to us, at least, is that there's this non-local rounding technique. And this hasn't been seen before in literature. And we think it might be useful for other problems. In particular, there's this problem called the min-sum k clustering, which has very similar properties. It's very sensitive. It has this nonlinear objective. And if you notice, there's like a nice web of connections between these problems. And so we connected aversion k clustering to local k-median. There's the facility location problem. And min-sum k clustering is very related to max k-cut. In some sense, it's the complement of max k-cut. So can we do something here? So this is perhaps the most interesting open question. Great. And that's it. Great. Thank you. So any questions? Yes?
The step 1 reduction of local k-median, how was that totally obvious from the beginning? Or that
it's actually not too hard, and I have an extra slide here. Thanks for asking. So in some sense, aversion k clustering, again, the problem is you need to make sure that in each cluster, the cost is what's the farthest each point has to travel. That's roughly the diameter, right? So that's roughly how far each needs to travel. So I'm going to just guess the diameter for every single one. I'll put a facility here. And the radius will be the diameter over 2. And I'll make sure every client in this radius has to travel d over 2 to reach this facility. Okay? So, in some sense, ideally, I would like to draw this in 3 dimensions because the facility is sort of up there. Everyone needs to travel d over 2, but the radius is also d over 2. So only a small fraction of clients can connect to this. So now notice that someone really far can't connect to this facility. And that's true in this clustering. Nobody really far belongs in this clustering. And everyone pays roughly the diameter. So what we do is we just guess every possible, there's only n log n such facilities. We just put all of them in there. And then that's the local k-median instance we saw. Okay, great. Any other questions?
Did you study, or is this related to min-sum of radii?
It is, in some sense, they're both min-sum of radii is a little nicer because in this algorithm, if you have too many clients in a cluster, adding another cluster, adding another point, can change it and it depends on how many clients there are. But min-sum of radii does not have this property. It doesn't matter how many points are in a cluster, it's just the total sum of the radii. But yeah, we looked into that and we tried to see if there's any connection, but they're only superficially connected as far as we can tell. Any other questions? Great. Thanks a lot.